Okay, I've got a problem up here on the board. I've drawn a picture here of my curve C. And so C is meant to be a quarter of a circle, quarter of the unit circle, going from 0, 1 to 1, 0. I would have to tell you that it's a circle because obviously there are lots of curves that connect those 2 points, but that is meant to be part of the unit circle. Notice it's oriented clockwise. And I want to do this integral of y squared dx. Okay. Now, there are a couple of ways I can do that. One is I can just remember how dx is going to switch over to dt. So I'm going to need to parameterize my curve. So I'm going to say r of t. Now, since we're going clockwise, I can't use cosine t sine t. There are a couple of ways to get to a clockwise orientation. I think the simplest is to use sine t cosine t. Now, as a general rule, switching x and y does not reverse the orientation. But for a circle like this, it actually does. Notice if t is 0, I would be at 0, 1. Oh, that's convenient. So when I parameterize with sine as the x component, this isn't my starting point, this is. By the time t is pi over 2, I'm going to be at 1, 0. So that's very nice. Okay. And so then I could say, okay, so this is going to become the integral from 0 to pi over 2. I've got to express my integrand in terms of t. So y was cosine of t. Remember, this is just giving me x, and this is giving me y. So that's going to become cosine squared t. And then dx is x prime dt. So if I were to look at r prime of t, that would be cosine t negative sine t. This right here is my x prime of t. So I'm going to multiply this by a cosine of t dt. Now, what I'm doing there is I'm just sort of remembering what the scaling factor is when I switch from dx to dt. In a moment, I'll write down sort of what all the different possibilities for the scaling factors are, but I'm also going to show you another way of doing this problem if you're not crazy about this notation, okay? Because people are going to vary with what notation they prefer. All right, but this is the integral from 0 to pi over 2. I'm going to just rewrite that cosine squared as 1 minus sine squared times cosine of t dt. So I could have multiplied that out to get cosine cubed, but I'm remembering that the trick for integrating an odd power of sine or cosine is to separate out one factor to get absorbed into a du and rewrite the remaining even power in terms of the other trig function. So now I can say u is going to equal sine of t, so du is cosine of t dt, and so this becomes the integral from sine of 0 is 0 to sine of pi over 2 is 1 minus u squared du. That's going to be u minus u cubed over 3, evaluated between 1 and 0. So that's 1 minus a third minus 0. I'm going to get 2/3. Okay. So there's my integral right there. Okay. Now, let me just summarize again the scaling factors that we can have. So if I'm doing a line integral and I'm integrating with respect to s, the scaling factor is that that's going to give me the magnitude of r prime of t dt. If I'm integrating dr, that's the same as t ds, and that becomes r prime of t dt. No magnitude there, because essentially the t is r prime divided by its magnitude, and then the ds gives me a copy of that magnitude, and those cancel. Okay. If I have dx, that becomes x prime of t dt, and if I have dy, that becomes y prime of t dt. So here, I just used the fact that that was my scaling factor and went right to rewriting things in terms of t. I'm going to show you another option that I could do if I wanted to. And this is just because I sort of prefer the f dotted with t ds notation. So I can recognize that this integral right here is plus a 0 dy. So now I can recognize this as the dot product of y squared 0 with dx dy, and I can say, oh, okay, that's the force that I'm using to do a work integral. And then I can say, okay, this is the same as the integral along C of f dotted with t ds, which I know is going to be the integral. Let's see, I've erased my r of t. R of t we said was sine t cosine t as t varied from 0 to pi over 2. So this will be the integral from 0 to pi over 2. F of r of t would become y squared is now cosine squared t, comma, 0, dotted with r prime. Now that's r, so r prime is going to be cosine t negative sine t dt, and that takes me right to what we had a moment ago. Integral from 0 to pi, cosine squared t times cosine of t plus 0 dt. So I'll get to the same thing, but writing it this way, I just put it into the notation that I prefer for these sorts of things. So it's totally up to you how you do that, but just wanted to point out those options that you have. Okay, last thing I want to talk about is if we reverse the orientation of a curve. So let's say that C is a smooth curve, and it's actually okay if it's a piecewise smooth curve. You don't need it to come in one piece. I'm going to let negative C be the same curve with the opposite orientation. So it's the same set of points. So if this is C, the opposite of C would still be the upper right quarter circle. It would just be going counterclockwise instead, so from 1, 0 to 0, 1. So same collection of points in 2 space or 3 space, depending where we are, in this case 2 space, but oriented in the opposite direction. Okay. If I have an integral of, I'm just going to write these in 2 space, all of this extends to 3 space. If I had just a regular line integral, so this doesn't involve any vector fields, this is just a plain old regular line integral of a function, this is going to be exactly the same as if I did the same line integral over C. Switching the orientation does not affect the value of the line integral. Okay. The reason for that, notice I've got exactly the same integrand here. And ds, when I switch it to dt, ds is always positive. So what's happening is if I'm going this way, this is the positive direction. If I reverse the orientation so that I'm going this way, I redefine that this way is the positive direction. So if we're just doing a plain old regular line integral, we're always moving in the positive direction. ds is always positive, and so I'm integrating the same thing with respect to an arc length that's always positive. I get the same thing. Okay. However, if I integrate and do a work integral along a curve with the opposite orientation, that is going to give me the opposite value. Okay. We talked about this a little bit before. Common sense, again, tells me that riding my bike into the wind is a very different experience from riding my bike with my back to the wind. Okay. So I'm going to have a different experience. The force field is going to have a different effect on me. So it seems at first like this is violating this rule until you recognize that the integrand here contains the unit tangent vector. And when you reverse the orientation, that reverses the sign in front of the unit tangent vector, because it's going to reverse the direction in which that is pointing. So that's where that negative sign comes in, from the fact that when we reverse the orientation, this t is tangent to negative c, this t is tangent to c, and they point in opposite directions. Okay. Now, what that means is if I'm integrating along c, some function dx, integrating along negative c, if I reverse the orientation of my curve, that's going to give me the opposite of the integral along c of f of xy dx. Okay. So ds is defined so that it's always positive. But with x, we define that moving to the right, or if we're in free space, moving forward is the positive direction. So if I reverse the orientation, and I was going right, and now I'm going left, now I'm going in the negative direction. Okay. And we can sort of see this reflected in the scaling factors, because when I switch from dx to dt, I'm multiplying by x prime, which is a signed quantity. So if I reverse the orientation, that scaling factor is going to reverse sign. Okay. Same thing with this, t and r prime. If I reverse the orientation, that reverses the sign of that, well, vectors don't have signs, but that reverses the direction of that vector, essentially multiplying it by -1. Okay. Same thing again with if I were doing a line integral with respect to y, or in 3 space with respect to z. So the one that does not, where changing the orientation doesn't affect things, is if I'm just integrating a real valued function with respect to arc length, we just define arc length is positive in the direction of the orientation. But if I'm doing a work integral, or if I'm doing an integral with respect to x or y or z, which often show up in work integrals, then reversing the orientation will reverse the value of the integral. And I think that's nicely reflected in what these scaling factors are, because here reversing the orientation will not change the sign of the magnitude of the derivative, but it will change the direction of the derivative, and it will change the sign of these individual derivatives. Okay, that's it for 16.2.